Good afternoon to everybody. Today we'll be doing the comparator design. So we have already done the op-amp design. So it's the same. First we'll be starting with the two-stage comparator design. Let me draw the circuit. It is almost the same as an op-amp, what we have done previously. So the basic thing you see that it is almost the same as a two-stage op-amp, but the only thing that is different here is we don't have the compensation capacitor. Since here we'll be mainly using the comparator in open loop, so we don't need the compensation capacitor. Now let us name these transistors. So the gain will be like what you have done in the two-stage op-amp case. You can write this V plus V in minus, so it will be GM2 by GDS2 plus GDS4, it is the gain of the first stage, into GM6 by GDS6 plus GDS7. So we see that we can represent this as an amplifier having just two poles. So it can be written like AVS equals to AV0 by S by P1 plus 1 S by P2 plus 1. So what we have to do is we'll first try to find out the propagation delay of this two-stage comparator. So we'll give us step input and we'll try to find out the step response. Okay. So done. So what we can write this one as and since we are finding the step response, we can write this again as V in by S, we are giving a step response. So if you okay, sir. So in time domain we can write this as so let us assume that we'll be assuming that the P2 is the P2 is greater than P1. So if say M equals to P2 by P1, we can write V out equals to AV0 minus 1 to the power and also say T equals to so what next we have to find out the dVdt so that we can find out what is the maximum slew rate limitation on this. So first find out dVdt or rather dV out by dTn. This will be to find out maximum of dV will again differentiate this. Set this to 0. We get So this is the maximum possible dv out by dt that is permissible in the comparator. So if we are given for a given load capacitance, and if we know the current, then we can find out, we have to find out the slew rate, and if dv out dtn becomes this maximum value becomes greater than this, so you know that the comparator is working in the slew limited region. Next will be finding out the total propagation delay. So we have seen from this, we can write V out in this fashion: AV0 Vn 1 minus, we'll break this into the exponential term, that is 1 minus Tn plus Tn square by 2 . Now for finding out the propagation delay, we can set, either say the comparator is moving between these two. So this is the plot, typical plot of a comparator. This is input voltage, and VOH is the highest possible output voltage, VOL is the lowest possible output voltage. So so for finding the propagation delay, we can take the 50% of these two values, 50% of VOH, this range. This we can consider if the output swings from 50% of VOL to 50% of VOH, then we can consider it as the propagation time. So in place of V out, we'll replace it by VOH minus VOL by 2 equals to AV0 into V in by 2 into mTn square. So Tn will become VOH now we can define V in minimum as total output range in which the comparator can operate by its gain. So we'll define V in min by this. So using this here, we can get the propagation delay as roughly V in this V in minimum by V in, this represents that is V in rather represents how much overdrive we are giving to the comparator. So this ratio is inversely proportional to the overdrive. Normally we will be operating the comparator, we will be giving the input to the comparator as some more, as a higher factor than we need for than V in minimum, maybe 10 times overdrive or more. So the propagation delay will be given by this. And if the comparator is operating in the slew rate limited region, so we can know the slew rate is given by I by CL. So we can find out this one, that slew rate can be written as delta V by delta T equals to I by CL. Delta T will be delta V. This will be the delay when the comparator is operating in the slew rate limited region. So next, there can be other variations of the comparator topologies, like we can have a push-pull output source using that one only. This is another variation of the comparator topology. Here we are using a push-pull output stage for obtaining higher current sourcing or sinking. Additionally, but the problem with this stage is that the gain is low due to this diode connected loads. So the gain of the first stage will now be given by, say if we write this as M3, M1, M2, M6, M7 like this. The first stage gain, it will be given by GM1 by GM, say GM4, gain of the first stage. Compared to the gain of the other stage, this gain is low because of this GM4. So there can be another alternative. Say we could use a cascode. We could use a cascode source, but cascode is not used, not preferable here, because whenever we are using the cascode source, the resistance gets increased. So the output pole, output pole is given by 1 by R into C. If this resistance increases, this value will decrease. So the total bandwidth will decrease. The comparator will not be working first. So cascode stage is generally not preferable. So now the comparator has some comparator to improve the performance. Next, we could be using an auto zeroing technique. What happens in a comparator is, even if you are applying this same voltage to both the input sources, the output won't be zero. There will be some value in the output. It is because of the offset, input offset. So we represent this input offset as, say, another voltage source connected in series with one of the terminals. The polarity is not important. It can either be a positive or negative. So in auto zeroing technique, we'll be trying to remove this offset. So there are two ways of removing this offset. Say first, if we connect capacitor C so in the first phase, we are connecting the comparator in this fashion. So since this is VOS, the terminal here, it is at VOS in the positive terminal, and so the output here, this will also be at VOS. So the total voltage across the capacitor will be VOS. Now if in the next phase we connect this capacitor like this, in this fashion, say connect this in series with the VOS voltage source, this same capacitor, and we say ground this one. So the offset voltage will be nulled by the voltage stored across the capacitor, since in the previous phase the voltage stored was exactly equal to the input offset. So you can combine both these two structures and use one find and do the final auto zeroing structure. So we'll be using 2 clock phases for this. In the first phase, this one will be on, this one will be on, and this one will be on. And in the next phase, phi 2, this two will be on. So this combines these two structures. So if we use this sort of technique, it will take care of the input offset. So another would be performance improvement technique would be use of hysteresis. Oh, auto zeroing technique is, you see, before we'll be having an input offset in the comparator. When if we connect both the two inputs at same value, say we are joining both the positive and negative terminals, so the output should be 0. But due to the input offset, there will be a small voltage at the output. So this is referred to as the input offset. So for cancelling the input offset, what we do is in one phase we connect this as a buffer, and then we use this capacitance. This VOS is just a model; it is not actually connected. So what here it is at 0 volt, 0 potential, but due to the offset, the potential here will be VOS. So due to the buffer position, this capacitor will get charged to VOS. So if in the next phase we connect this in series with this positive input terminal, it will, sum of these two will be 0. So it will remove the input offset. So in this third figure, we are combining both these two. In phi 1 clock cycle, the capacitor will get charged to VOS, exactly the potential of the input offset. And in phi 2, when you are applying the input, this capacitor will make the input offset, effect of input offset 0. Now for say we have a noise, say we have a sine wave, we are applying this to the input of a comparator. 0. When in presence of noise, there will be some small perturbations upon this, like due to noise, this sine wave will become distorted like this. So if the comparator is a very perfect high speed comparator, whenever there will be at this position, say this is the 0 potential line and the sine wave is like this, it is due to the noise, the voltage here becomes like this. So there will be some unintended transitions of the comparator. it will comparator output voltage will behave like this at in these positions. So if we use hysteresis, then we'll have a margin for reducing these errors due to noise. So if we have hysteresis, it will be like this. Here we are plotting V in. Here we are plotting the output voltage V out. So when V in first start, in case of a sine wave, say, or any other wave, when it first starts to increase, it will increase, say, up to some value. Say this is VTR trip plus. Then when it reaches this value, V out becomes equals to VOH, the maximum possible output voltage. Now when when V in is decreasing, it will not trigger at this value, at this voltage. It will move up to this position. V in will decrease. Then after this, it will again come back. So since the positive and negative trip points, they are not same, so we'll have this margin against noise. So if we had applied hysteresis in case of this noisy signal, say if the positive trip point was here and the negative trip point was here, so let me draw it again. So when input crosses this VTRP, the output will rise. It will stay here. It will not make a transition here. Only when the input falls below, it will come below VTRP minus, then it will make a transition to VOL. Similarly, it will again go on until the input moves up to VTRP plus. Then it will again, the output will make a transition to VOH. So we'll see that it is not affected by noise. So in the comparator, there are two ways of including hysteresis. One is external, and is internal. By external, we mean that we have already designed the comparator. Then now we will be using some method, some extra circuit to remove hysteresis. And by internal, it means that the hysteresis circuit will be inbuilt within the comparator. Now for doing external hysteresis, we have a comparator circuit like this. For this circuit, say V in initially, consider V in is very low, so the output will be, say initially V in is low, output will be at VOH. Now say V in is increasing. When V in becomes equal to the voltage at the positive terminal, then after that, if V in becomes more than the voltage at positive terminal, then V out will switch. So this is the positive trip point. So the potential at the Vx is given by V out into R2 by R1 plus R2. So VTRP plus will be given by VOH. Similarly, for finding the negative trip point, VTRP minus will be given by VOL into R2 by R1 plus R2. So the total hysteresis, this width of the hysteresis curve, this width, it will be given by R2 by R1 plus R2. So the wider this is, the more immunity you will have over noise. Next there will be the internal method of avoiding including hysteresis. So we'll start with the two-stage comparator structure. Here we'll be using one latch. So this M6 and M7, it acts as a latch. It provides a positive feedback. This one. So to ensure hysteresis, the positive feedback provided by this M6, M7, it should be greater than the negative feedback provided by M5. M5, and say assuming this it acts as an this positive feedback is greater, then we will try to find out the trip points. So initially, say we have connected the circuit like this. We are giving a fixed potential here at input of M1, and here we have connected a voltage supply V in. This is M5. So initially, say V in is very low, that is such that M2 is off at cutoff. So the total current will be conducted, say I, this is I. So I5, this will be, so I3 will be equals to, initially I3 equals to I1 equals to I5, and I6 will be given by W by L of 6, W by L of 3 into I3. This is the initial current when V in is low. Now as V in starts to increase, at some point of time M2 will get turned on. So then I6 will start flowing through M2. So as V in increases, gradually as V in increases, gradually total of I6 will flow through M2. So at the point when just M2 gets on and I6 starts flowing, that is the trip point. Similarly, for the other negative trip point, for calculating the negative trip point, we will be connecting V in here, and then initially this M7 and M4 they will be on, and M1 will be off, and as V in increases, then M1 will get on. Next one is design of high-speed comparators. This one, say when V will start to increase, at some point M2 will get on, then I6 will be flowing through M2. At this point, this is the positive trip point, and then as more and more of I6 will flow into M2, then M7 and M4 will also get on, and gradually this M3, M6 they will get off, and M1 will get off, as all of the current, all of I5 will start flowing through M2. So when M2 just gets on, that is the trip point. And similarly, for calculating the negative trip point, it will be, if we connect a voltage source here, and then we have to find out when M1 just gets on. Now next, there will be for a high-speed comparator, consists of two parts. First is the preamplifier, followed by a latch. Preamplifier is basically what you have seen those two-stage amplifier. It can also be a diff amp. Now a preamplifier has this type of negative this characteristic negative, and a latch will have, because a preamplifier is denoted given. If we can replace the preamplifier by single pole response, say like S plus P, so it will have this type of characteristic preamp, and this will be the characteristic of the latch. So what the preamplifier will do is it will first magnify the Vin plus and Vin minus. It will first magnify the difference, so that when this magnified difference come to the latch can easily pick up those and find out the difference. What we can do as preamplifier is, so this is basically the same as a two-stage comparator followed by a latch. But generally this structure has a problem of having lower gain due to this diode connection structure, and also what happens is that this output, this can directly come to the input. If the output changes very quickly, this can directly, by this, due to this CGD capacitance, a part of the output can directly come to the input. So there is no isolation between the input and output. So to fix these two problems of low current gain, can modify this structure. What we will be doing is we will connect additional PMOS capacitances here, so that it will supply the required current. It will supply the extra current required to increase the gain. And then to improve the isolation, there will be another set of NMOS transistors here, so that the output will be taken here, so that the output won't directly come to the input. Then this will be followed by another latch. So the gain can be increased by providing additional current through these transistors, say M5, M4, and the isolating the input from the output this care is taken by these two transistors. Additionally, it will be followed by this latch. So often for high speed comparator design, so 2 or 3 of these preamps can be cascaded with the latch. So this is the end of the comparator design class. Thank you.